Breathe softly and let your thoughts drift beyond the room around you, out past the sky, through the quiet shimmer of stars, and into the slow, eternal turning of the cosmos. Tonight we'll explore a simple truth that shapes everything you've ever known. Everything in the universe is spinning, from the smallest particles inside your body to the grand arcs of galaxies wheeling through the dark motion, is the language of existence itself. In this calm journey, we'll trace how the first ripples of creation gave rise to rotation, how stars, planets, and even life inherited their endless motion. Along the way, we'll discover why the universe turns, how that motion bends time, and how through every rotation it remembers its own beginning. So, take a slow breath. Let stillness meet motion. The story begins where time itself began, when the universe first learned to turn. Right now, your body feels still. Maybe you are lying down or resting in a chair, the weight of blankets or clothing pressing softly against your skin. The room around you seems quiet and unmoving. The floor feels solid, the air feels calm. But beneath this gentle sense of stillness, something vast is happening. The ground under you is part of a planet that is spinning once every day, turning from west to east like a slow, enormous wheel. At Earth's equator, that spin carries you along at roughly 1,000 miles per hour, a speed faster than the sound of a jet cutting through the sky. At the same time, the whole planet is racing around the sun at about 67,000 miles per hour, tracing a wide loop through space. And even that is only part of the story. The sun itself is moving through the Milky Way, and the Milky Way is gliding through the larger cosmic web. By the time you add all of these motions together, you are constantly traveling through the universe at unbelievable speeds, even as you lie perfectly still. There is a tiny spark of tension in that realization. If we are moving so quickly, why do we not feel it? Why is there no sense of rushing, no tug on the body, no wind in the face to untangle that feeling? Imagine yourself on a very smooth train. You are sitting by the window. The carriage glides forward at a steady speed, the wheels humming softly beneath you. If you close your eyes, you might almost forget the train is moving at all. Your drink rests calmly on the tray. The air is quiet. Your body feels as if it is at rest. It is only when you look out and see the landscape sliding past, or when the train slows or turns, that motion reveals itself. A gentle push presses you into the seat as it accelerates. A subtle lean tips you sideways as it rounds a curve. Your senses are tuned not to speed itself, but to changes in speed. This is the essence of inertia. When a body moves at a constant velocity in a straight line or in a smooth rotation, everything inside that system shares the motion. There is no internal jolt, no internal sign that anything is happening. You feel forces only when something speeds up, slows down, or changes direction. On Earth, you, the chair, the floor, the air, and the entire landscape are all caught in the same smooth spin. The rotation is steady, repeating day after day, year after year. You are like a passenger on a train, so perfectly built, with such gentle curves and long straight tracks that your body forgets you are traveling at all. Yet the planet does leave clues behind quiet signatures of its turning. In large weather systems, the Coriolis effect nudges storms into spirals, curling hurricanes, one way in the northern hemisphere and the opposite way in the southern hemisphere. Long ocean currents bend across the globe in graceful arcs, responding to the same underlying spin. But these patterns are too large and too slow for your inner ear to feel. They are the handwriting of rotation on the skin of the world, rather than a shove against your body. For a more direct proof, scientists built one of the simplest and most elegant devices in physics, the Foucault pendulum. In 1851, the French physicist Léon Foucault suspended a heavy metal bob on a long wire from the high ceiling of the Panthéon in Paris. When he set it swinging, the pendulum traced a straight line through the air. Yet as hours passed, that line seemed to rotate slowly across the floor. The plane of the swing stayed fixed in space while the Earth turned beneath it. Anyone watching could see it. The path of the pendulum crept around, marking the planet's rotation, without the need for any telescope or star chart. It was as if the building itself were silently revealing that it was pinned to a world in motion. Many science museums still host Foucault pendulums. If you have ever watched one, you might recall the hypnotic slow procession of its swing, cutting through sand or knocking over tiny pegs arranged in a circle. That gentle motion is the Earth's rotation made visible, the hidden turning beneath your feet, translated into something your eyes can follow. Even above the atmosphere, this idea of shared motion continues. On the International Space Station, astronauts appear to float freely, drifting in slow arcs through the module's water globules hanging in the air, like tiny clear planets. From inside, it would be easy to imagine that gravity has almost vanished. But the truth is more subtle and more beautiful. The station orbits Earth at an altitude of only a few hundred miles, where gravity is still quite strong, only slightly weaker than at the surface. Astronauts float, not because gravity is gone, but because they, the station, and everything inside it are all falling together. The spacecraft is in continuous free fall around the planet, moving forward so quickly that as it falls, the ground curves away beneath it. This shared falling creates the condition known as microgravity, where everything seems weightless because everything is accelerating together. Once again, it is not the speed that matters, but the change in speed. A stone, dropped from your hand on Earth, accelerates toward the ground while you remain on the surface, so you feel its weight tugging on your fingers. In orbit, both you and the stone accelerate at the same rate, and that difference disappears. The motion is still there, but the contrast is gone. Your body has nothing to push against, nothing to signal that you are perpetually falling around the world. Back down on the surface, the same principle keeps Earth's rotation hidden from your everyday senses. The planet's spin is incredibly steady. There are tiny variations influenced by the moon's tides, the shifting of the atmosphere, and the slow rebound of land that once lay under heavy ice sheets. But over the course of a single day, those changes are impossibly gentle. Your body cannot feel them any more than it can feel the slow growth of a tree. There is a related idea in physics called a reference frame. You can think of a reference frame as the viewpoint from which you are measuring motion. On the train, the interior is your reference frame. Within that frame, your drink is still, your seat is still, your body is still. Only when you look out the window and adopt the Earth as your new reference frame do you notice how quickly the train is moving. For most of our lives, we take the Earth as our default reference frame. The planet becomes our still background, and everything else is judged relative to it. Cars and planes, waves and clouds, birds and leaves. We notice only what moves differently from the ground. The deeper motions, like Earth's rotation and orbit, become part of the assumed backdrop. We are so used to them that we forget they are there at all. When you shift your perspective, though, the picture changes dramatically. Imagine looking down from far above the North Pole, watching Earth spin against a backdrop of fixed stars. Continents sweep by in long arcs. Night and day chase each other around the globe. The line between sunlight and shadow, the Terminator, slides slowly across oceans and cities. In this frame, the planet's rotation is obvious. A grand, unhurried swirl of blue and white. Now imagine pulling back even farther until the sun comes into view. You see Earth's path around it, a broad ellipse traced over a year. The speed is still steady, about 67,000 miles every hour. But from this vantage point, that smooth motion is unmistakable. The idea that Earth is stopped in space feels as strange as claiming that a spinning top is frozen. Our senses were not built for such scales. They evolved to keep us safe from falls and collisions, not to track the drift of planets. So we rely on instruments, pendulums, satellites, telescopes, to reveal the motions that lie beyond our natural reach. There is a quiet awe in recognizing how thoroughly we are carried along. Every breath you take happens on a planet turning beneath a star, its spin inherited from the cloud of gas and dust that formed the solar system long ago. The angular momentum of that ancient cloud has never completely gone away. It has simply been rearranged into the rotations of worlds and moons and rings. You are part of that story, riding the momentum of events that began billions of years before you were born. Yet for all this grand movement, your daily experience remains gentle. The bed does not lurch with each rotation. The walls do not shudder as Earth races along its orbit. The continuity of the motion turns it into something like a background hum, a steady note so constant that your mind no longer hears it. If you let that thought settle for a moment, it can be strangely comforting. You are wrapped in motion so smooth that it feels like rest. The universe has arranged its great spinning structures in such a way that here, on this small patch of rock and air, you can lie down, close your eyes, and feel safe. There are no sharp corners in Earth's rotation, no sudden stops in its orbit. Only an endless patient turning. Still, one question remains, floating quietly beneath the surface of everything we have just explored. If we are carried by this motion so completely, where did it come from? Inertia can explain why the spin continues. Shared reference frames can explain why we do not feel it. Pendulums and space stations can reveal that the rotation is real. But none of these things alone answer the deeper mystery of how the universe first began to turn. To approach that question, we have to step even further, back beyond Earth, beyond the solar system, to a time when there were no planets or stars at all. We must return to the earliest moments after the universe itself was born, when there was only energy and the first tiny ripples in the fabric of space and time. It is there in that newborn cosmos that the seeds of every spin were sown. And so as you rest within Earth's hidden motion, carried effortlessly through the night, our journey will follow that thread backward to the moment when the universe first learned to twist and the great turning began. To understand why everything around you is spinning, now we have to travel back to a time when there were no planets, no stars, and no galaxies, no oceans rolling under moonlight, no trees swaying in the wind, not even atoms yet. Only a newborn universe so young that it did not yet know what it would become. In the standard picture of cosmic history, the universe began in an extremely hot, dense state and then expanded. In those first instants, space itself was packed with energy. Temperatures were unimaginably high, and distances were squeezed smaller than the tip of a pin. There were no stable structures, no orbits, no spinning worlds, just a seething, glowing fog of energy, and the tiniest particles appearing and vanishing in a blur. At first glance, that early universe sounds almost perfectly smooth, like a featureless mist. But at the very smallest scales, nature never holds entirely still. Quantum physics tells us that even empty space is restless, filled with temporary flickers of energy that pop in and out of existence. In the first fractions of a second, those tiny fluctuations were present everywhere, embedded in the fabric of space itself. Then something dramatic happened. Cosmologists call it inflation, a brief period when the universe expanded at an astonishing rate, doubling in size over and over again in a tiny sliver of time. During this phase, those quantum ripples were stretched out from subatomic scales to cosmic ones, frozen into the growing universe as faint variations in density. Regions that were ever so slightly denser became seeds, the earliest hints of where matter would later gather. You can imagine it like this picture: a calm pond with tiny ripples barely visible on the surface. Now, suddenly stretch that pond until it is the size of an ocean, then a world, then a galaxy. The once small ripples become vast ridges and valleys in the water. Inflation did something similar to the early universe, magnifying microscopic quantum jitters into macroscopic patterns. From those patterns, everything we know would eventually emerge. Where there was a little more matter, and energy gravity pulled harder. Over millions, then billions of years, those slightly denser regions drew in more material, forming clouds, then stars, then galaxies. And as those clouds collapsed under their own gravity, they began to spin. This is where an important idea enters the story: the conservation of angular momentum. When something collapses inward, any slight twist it has tends to get amplified. Think of a figure skater pulling in their arms. As they draw their mass closer to their axis, they spin faster. They are not creating new spin out of nowhere. They are conserving the angular momentum they already had, concentrating it as they take up less space. So the universe did not need someone to start it spinning. The rules of physics allowed small imbalances in motion to grow naturally into the rotations we see now. Those rules were present from the beginning, encoded in the way space, time, and matter behave. We can still see the fingerprints of those early fluctuations today, in the cosmic microwave background, the faint afterglow of the Big Bang. This light, stretched into microwave wavelengths by billions of years of expansion, fills the universe almost evenly from every direction, but not perfectly evenly. There are tiny variations in temperature and density across the sky, subtle mottlings like the grain in old paper. Those patches map the original ripples inflated from quantum scales to cosmic scales, the very same irregularities that would later give rise to galaxies and clusters of galaxies. Some studies of this cosmic afterglow have suggested that there might be very slight, large-scale alignments or asymmetries, patterns in which certain directions in the universe seem to be a little different from others. Researchers sometimes refer to one such possible alignment as a kind of cosmic axis. Whether these features are real or simply chance arrangements in the data is still being debated, but they hint at a question that stirs the imagination. Could the universe as a whole possess some grand rotational character, some faint directional memory from its earliest moments? We do not yet know the full answer. What we can say with confidence is that on smaller scales, rotation seems to be a natural, almost inevitable outcome of gravitational collapse and the conservation of angular momentum. Given a cloud of matter in a universe governed by our laws of physics, it is very difficult to avoid spin. The slightest unevenness, the tiniest non-zero twist in motion will grow as the cloud shrinks. If you could watch the universe speeded up in a time-lapse that spans billions of years, you would see this process unfold like the blooming of flowers in a cosmic garden. At first, there is only a glowing fog, almost uniform. Then faint threads and nodes appear, the result of gravity pulling matter into a web-like structure. Within those knots, matter swirls inward, gaining rotation as it collapses. Galaxies ignite their stars, orbiting their centers in vast, slow circles. In a very real sense, the spin of Earth itself is a continuation of a story that began long before our planet existed. The rotation you do not feel under your bed tonight is linked by a chain of gravitational events to the earliest motions of matter in the universe. When you think about Earth like that, as a small spinning memory of ancient cosmic flows, its everyday turns from day to night feel a little less ordinary and a little more sacred. Of course, the universe is not perfectly orderly. Alongside the elegant laws that predict the growth of spin, there is chance collisions, tidal interactions, and complex gravitational tugs can speed up, slow down, or even flip the rotations of individual objects. Some planets spin in the opposite direction to their neighbors, likely due to giant impacts in their early history. Some galaxies collide and merge, scrambling their stars into new configurations. The universe is not a clockwork machine, wound once and left unchanged. It is more like a dance guided by rules, but open to improvisation. Still, underneath that complexity, the foundational pattern remains the early universe's tiny imbalances, evolved into the grand rotations we see now. Spin is not an add-on. It is a natural outcome of how gravity and motion work together in an expanding cosmos. As you rest and picture those first moments, the fog of energy, the sudden inflation, the stretching of ripples into vast structures, you might feel a mixture of curiosity and awe. The tension of not knowing exactly what happened at the very beginning is softened by the calm clarity of what we have learned since. We may never see the universe's birth directly, but we can read its traces in the light that still bathes us from all directions, and in the way everything, everywhere, continues to turn. Take a slow breath and let that image rest in your mind, a universe that began nearly uniform, almost featureless, but not quite. Those tiny departures from perfection, pushed and pulled by expansion and gravity, became the galaxies, stars, and planets we know. They became the rotation of Earth, the spin of atoms in your body, the spiral structures you can see on a clear night if you look far enough. The hidden motion beneath you now is not just the spin of a single planet. It is the echo of the universe's earliest stirrings, carried forward through billions of years of cosmic evolution. And in that realization, another gentle question arises, ready to guide us forward. If the universe's spin helped shape the largest structures in existence, what role does rotation play in the delicate conditions needed for life itself? That is, where our journey will drift next, toward the quiet heartbeat of a spinning world, and the ways in which the turning of a planet can cradle oceans' climates, and the soft miracle of living things. If you step outside on a clear evening and look up, the sky above you feels steady. The stars do not seem to hurry. The moon moves so slowly that over a few quiet minutes it might as well be frozen. Yet beneath that apparent stillness, Earth is turning with a rhythm that quietly shapes almost everything about your days, your nights, and your life. Earth completes one full spin in about 24 hours. Relative to the distant stars, that rotation takes just under that span, about 23 hours and 56 minutes. But for us on the surface, what matters is the steady beat of sunrise, midday, sunset, and night. Wikipedia +1. That turning is not an abstract astronomical detail. It is the clock that sets the length of a day and the canvas on which your entire experience of time is painted. Imagine the planet suspended in space, half of it lit by the sun, half wrapped in darkness. Because Earth spins the boundary between day and night, slides across oceans and continents like a slow, soft wave. As your location rotates into the light, dawn arrives. As it turns away, evening falls. Without rotation, there would be no familiar cycling between brightness and darkness. Only a world split into two extremes, one face locked in eternal day, the other in endless night. Earth's spin softens that harshness, because each place on the planet moves in and out of sunlight in a regular rhythm. Heating and cooling are shared. Morning warmth has time to build, but evening brings a chance for the surface to release its stored heat. Over many cycles, this steady alternation helps create climates that are neither all scorching nor all frozen, but something gentler, capable of supporting oceans that do not boil away, and landscapes that do not freeze beyond recovery. Rotation also plays a crucial role in how air and water move. As Earth spins, points near the equator travel faster than those near the poles, simply because they have farther to go in the same amount of time. That difference in speed leads to the Coriolis effect, a subtle deflection that influences the paths of winds and currents over long distances. Large storms like hurricanes and typhoons swirl because of this effect, their clouds wrapping into graceful spirals around low-pressure centers. Ocean currents bend and arc, redistributing heat across the globe. Without rotation, air would rush more directly from equator to pole and back again, and ocean flows would be simpler, more linear. With rotation, the patterns become richer, layered, and dynamic. These complex systems carry warmth to higher latitudes and coolness toward the tropics, smoothing out temperature differences and creating diverse climates in which many kinds of life can flourish. Deep inside Earth, rotation adds another layer of protection. The planet has a molten outer core, rich in iron and nickel, that moves and churns. Combined with Earth's spin, this motion generates a vast magnetic field that surrounds the planet, forming a protective bubble called the magnetosphere. When charged particles stream from the sun as solar wind, this magnetic shield deflects most of them, preventing them from stripping away our atmosphere and damaging living cells with high-energy radiation. We sometimes catch a glimpse of that invisible shield in motion when solar particles slip into Earth's magnetic field near the poles and collide with atoms in the upper atmosphere. The result is the aurora curtains of green and red light shimmering in polar skies, a ghostly dance powered by the interaction between solar storms and our planet's magnetic heartbeat. Without that shield and the rotation that helps sustain the core's motion, Earth would be far more exposed, more like Mars, whose weaker field allowed much of its early atmosphere to be lost to space. Rotation does not act alone, of course. Distance from the sun, the thickness and composition of the atmosphere, and the presence of liquid water all play vital roles in making a planet habitable. But Earth's spin threads through all of these factors, shaping how energy flows, how weather develops, and how long-term climate settles into stable patterns. It can be helpful to see this more clearly by looking at other worlds. Venus, similar in size to Earth, and not dramatically closer to the Sun, offers one striking comparison. A day on Venus, one full rotation on its axis, takes about 243 Earth days. Not only is the rotation extremely slow, it is also retrograde, meaning Venus spins in the opposite direction to most planets, including Earth. Combined with a dense carbon dioxide-rich atmosphere and powerful greenhouse effect, this sluggish spin contributes to a world where the surface temperature stays around 860 degrees Fahrenheit, hot enough to melt lead. Thick clouds trap heat, and with such long days and nights, there is little break in the relentless warming. Mars, on the other hand, spins at a rate similar to Earth's. A Martian day is only slightly longer than our own. But Mars is smaller and has lost much of its atmosphere and magnetic field. Its thin air and weaker greenhouse effect make for colder temperatures on average, and without a strong magnetic shield, the solar wind has been able to chip away at its atmosphere over billions of years. The result is a world that may once have supported rivers and lakes, but now lies mostly dry and barren, its surface exposed to radiation that would be harsh for unprotected life. From these comparisons, a subtle picture emerges. Spin alone does not guarantee a gentle world, but it is deeply entwined with the other factors that matter. Earth happens to sit at a distance from the sun, where water can remain liquid, with an atmosphere thick enough to carry heat, but not so thick as to smother. Its rotation is fast enough to prevent extreme temperature contrasts between day and night, but not so fast that winds become constant violent gales. Its spinning core generates a magnetic field strong enough to guard the atmosphere that protects us. In this sense, rotation is like the tempo in a piece of music. The same notes played far too quickly or far too slowly can become chaotic or dull. There is a range where movement feels natural, where patterns can form without collapsing. Earth's day length is not perfect in any absolute sense, but it sits in a comfortable band where the rhythms of weather, water, and life can align. Life on Earth has grown up inside this rhythm. Over hundreds of millions of years, organisms have evolved internal clocks, circadian rhythms, that resonate with the planet's 24-hour cycle of light and dark. In humans, these clocks live in clusters of neurons, deep in the brain, responding to cues from sunlight, temperature, and social activity. They help regulate sleep and wakefulness, hormone levels, body temperature, and countless other processes. Plants open and close their leaves in sync with the day. Many animals hunt at dawn or dusk, tuned to the changing light. Some migrate with the seasons themselves, guided by the tilt and orbit that Earth's spin helps define. Even when taken into constant artificial light, many living systems continue to show roughly 24-hour cycles, as if the memory of the planet's turning is etched into their chemistry. When you begin to feel sleepy at night, that sensation is not an accident. It is the echo of Earth's rotation, translated through biology into yawns, heavy eyelids, and the pull of rest. Your internal clocks have been shaped by countless generations of ancestors who lived under the same spinning sky. Even when you are indoors, far from the direct glow of sunrise and sunset, those rhythms hum quietly within you, aligning you with the world's day-night heartbeat. There is a moment each morning when the first rays of sunlight slip over the horizon, and a moment each evening when they slide away again. These transitions, dawn and dusk, carry a particular emotional weight. They are times when the sky changes color, when shadows lengthen or dissolve, when the air seems to pause. Those shifts are direct expressions of Earth's rotation brought into human timescales that you can feel and watch. If Earth spun significantly faster, days would be shorter, perhaps only a few hours long. The sun would whip across the sky. Mornings and evenings would flash past in quick succession. The atmosphere would likely respond with more intense and rapidly changing winds, and the planet might bulge more at the equator due to the increased centrifugal effect. If Earth spun much more slowly, days might stretch into weeks or months. One side of the planet would bake under prolonged sun, while the other cooled under extended darkness, placing much stronger demands on any life trying to adapt. Instead, Earth's rotation sits in a middle ground, where living systems can anticipate regular changes without being overwhelmed by them. The predictability of sunrise and sunset, the gentle pacing of weather patterns, and the stability of long-term climate. All of these are influenced by how the planet turns. There is comfort in the thought that as you move through your day, you are participating in this cosmic rhythm. Every time you open your eyes to daylight or close them in darkness, you mark another partial turn of the world. Every meal, every conversation, every quiet moment of rest fits into a sequence of rotations that has been going on for billions of years and will continue long after our particular era has passed. If you listen closely, perhaps you can almost feel it, not as a physical tug, but as a gentle sense of order. Morning follows night, night follows day. Seasons roll in a familiar pattern, linked to the tilt of Earth's axis and its journey around the Sunday. The planet's spin lies at the heart of this dance, giving time its daily rhythm and climate its broad strokes. As you lie still and breathe, your heart beats with its own steady tempo, a smaller echo of Earth's turning. Blood moves through your veins as air moves through the atmosphere and water moves through the oceans. In countless ways, your body mirrors the planet that carries you a nested set of rhythms within a larger planetary pulse. And yet, as we have seen, this gentle spin is not only about comfort, it is also a trace of something older and bigger, the angular momentum of collapsing clouds, the inheritance of a universe that began long ago with tiny fluctuations and expanding space. Earth's rotation is the local expression of a cosmic habit, a preference for motion over stillness, for turning over standing still. Our journey, though, is not finished. We have seen how spin cradles life in a gentle balance of light and dark, warmth and cold, protection and exposure. But rotation does something even stranger and more profound than shaping weather and sleep. It can reach into the fabric of reality itself, tugging on time, bending the flow of moments in ways that challenge our deepest intuitions. To follow that thread, we will have to look again at spinning worlds and stars, not just as habitats for life, but as engines that can twist space-time. From our calm vantage point under Earth's sky, we will take another step outward into a realm where rotation is not only the heartbeat of life, but also a subtle shaper of time itself. You have already met Earth's spin as something gentle and familiar. It gives you sunrise and sunset seasons, and tides the subtle pacing of your days. But rotation does more than move oceans and turn the sky. When you look closely enough, it reaches into something deeper and stranger, the flow of time itself. For a long time, people thought of time as an invisible river that flowed the same way everywhere, no matter what the universe was doing. A second on a mountaintop, a second deep in a valley, a second by a quiet lake or beside a roaring volcano. These were imagined as perfectly identical beads on an endless, unchanging string. Then came a new picture. In the early 20th century, Albert Einstein suggested that space and time are not separate things, but parts of a single fabric space-time. In this view, mass and energy do not just sit in space-time. They bend it. A massive body like Earth curves the geometry around it, and that curvature tells other objects how to move. A falling apple, a satellite in orbit, even a beam of starlight, are all following the natural paths laid out by this curved fabric. One consequence of that curvature is that time does not tick at the same pace everywhere. Near a massive object, clocks run a little more slowly than they do farther away. A clock on the ground deep in Earth's gravitational well will tick slightly slower than a clock on a high mountain or on a satellite in orbit. The difference is tiny, but it is real, and it has been measured many times. This alone is enough to make time feel less absolute. But general relativity holds a further surprise one that appears only when mass is not just present, but spinning. When a massive body rotates, it does more than curve space-time. It twists it. The rotation drags the fabric of space-time around with it, like a spinning ball pulling the surrounding water into a slow swirl. This effect is called frame dragging, or the lens. Thirring effect, named after the physicists who first described it in the early 1900s. Around Earth, this twisting of space-time is incredibly small, a delicate whisper layered on top of the stronger effect of ordinary curvature. For decades, it remained only a prediction on paper, too subtle to pick out from the noise of real measurements. But physicists are stubbornly patient. Eventually, they built an experiment sensitive enough to listen for that whisper. That experiment was called Gravity Probe B. Launched into orbit in the early 2000s, it carried some of the most precise gyroscopes ever constructed, near perfect spheres of fused quartz, spinning in vacuum. These gyroscopes were aimed toward a distant guide star. If space-time around Earth were perfectly static, the spin axis would point in the same direction forever. But general relativity predicted two tiny drifts, one due to Earth's mass curving spacetime, and one due to Earth's rotation dragging spacetime around with it. Over the course of a year, the frame dragging effect was expected to tilt the gyroscopes by only a few dozen milliarc seconds, an angle so small that it is comparable to the apparent width of a human hair, seen from many miles away. After years of painstaking analysis, the team reported that they had indeed seen the predicted drift within the limits of experimental uncertainty. Their gyroscopes had felt the twist of Earth's rotation imprinted into space-time and had quietly followed it. Around Earth, the twist is far too small to disturb your daily life. Your watch does not suddenly slip out of sync because of frame dragging. The tiny time differences that matter for navigation systems like GPS are dominated by the basic curvature of spacetime and the speeds of the satellites, not the planet's spin. But the very fact that we can measure the effect at all suggests that in more extreme environments, it might become much stronger, strong enough to shape the behavior of matter and time in dramatic ways. To glimpse those environments, we journey outward beyond our gentle planet to some of the universe's most intense spinners. Consider a star, many times more massive than the Sun. When it exhausts the nuclear fuel in its core, it can no longer support its own weight. The core collapses inward with tremendous force. If the mass is great enough that collapse ignites a supernova, an explosion bright enough to briefly outshine a galaxy, after the outer layers are blasted away, what remains is a neutron star, a sphere of matter so dense that a teaspoon of it would weigh more than a mountain. Because of the conservation of angular momentum, the collapsing star's rotation speeds up as it shrinks, just like a figure skater spinning faster when pulling in their arms. Many neutron stars rotate rapidly, turning once every fraction of a second to every few seconds. Those that emit beams of radiation from their magnetic poles sweeping across our line of sight are known as pulsars. To a radio telescope, they appear as precise repeating blips, pulse, 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 over and over again. Some pulsars, especially the so-called millisecond pulsars, spin hundreds of times each second. Their pulses arrive with a regularity that rivals, and in some cases approaches the stability of the best atomic clocks on Earth. In these objects, spin is not a gentle background feature. It is the defining characteristic of their identity, the reason they shine in such an ordered, periodic way. The spacetime around a neutron star is extremely curved compared to Earth's due to its intense gravity. The rapid rotation adds a strong frame-dragging component, twisting spacetime much more noticeably. A gyroscope orbiting such a star would precess far faster than one near our planet. Light rays, too, would feel the twist, their paths bent not only by gravity, but by the rotation of the mass generating that gravity. Even this, though, is only a prelude to the most extreme example of time-bending spin, the rotating black hole. A black hole is what remains when gravity overwhelms all other forces and collapses matter into a region from which not even light can escape. For a non-rotating black hole, the spacetime outside is described by a simple solution to Einstein's equations, the Schwarzschild geometry. For a rotating black hole, the solution is more intricate, known as the Kerr geometry. In the Kerr picture, the black hole has an event horizon, the famous boundary beyond which escape is impossible. But outside that horizon lies another region called the ergosphere. Within the ergosphere, frame dragging is so strong that nothing can remain stationary with respect to distant stars. Any object, or even any stationary point defined by spacetime itself, is compelled to co-rotate with the black hole. The rotation of the mass has so thoroughly twisted spacetime that the idea of simply hovering in place loses its meaning. In this region, time and space trade roles in subtle ways. Paths that might have been possible in a non-rotating space-time become forbidden, while new exotic ones open. Energy can, in principle, be extracted from the black hole's spin through clever processes that exploit the dragging of space-time. Theoretical work has suggested that the incredible jets of particles seen streaming away from the centers of some galaxies may be powered, at least in part, by frame dragging near supermassive, rotating black holes. Close to such an object, time dilation becomes extreme. A clock hovering just outside the event horizon of a black hole, especially a massive one, would tick much more slowly relative to a clock far away. If that black hole is spinning, the details become richer still as the interplay of curvature and frame-dragging shapes how different paths through space-time compare. From the viewpoint of a distant observer, processes near the horizon seem to slow and freeze. From the viewpoint of something falling in time feels normal, but the outside universe appears speeded up, compressed into a brief, bright history. Of course, you and your everyday life are far from these exotic places. There are no black holes next door, no neutron stars hovering near our sky. The distortions of time you experience from gravity and motion are small. A clock on a satellite might gain or lose a fraction of a second over many days, if its time dilation were not corrected, but those corrections are understood and quietly applied, allowing navigation systems to work with remarkable precision. Still, the existence of frame dragging around Earth neutron stars and black holes tells a single coherent story. Time and space are not rigid stages on which the universe plays out indifferent to the movements of mass. They are flexible, responsive, shaped by what happens within them. When something spins, it not only turns in space-time, it subtly draws space-time into its turning. There is a kind of wonder in realizing this while you lie still and listen. The rotation of the planet that carries you is twisting space-time in a way so small you will never personally notice it. And yet, the same underlying principle applied in more extreme environments can power jets from galactic cores and set cosmic clocks in neutron stars. The laws do not change, only the intensity of their expression does. You might think back to your own sense of time passing, the slow drift of days, the quicker flurry of hours, the nearly timeless moments when you lose yourself in thought or rest. On the scale of human feeling, time is already elastic, stretching and compressing in our perceptions. General relativity adds another layer, reminding us that even in strict physics, time is not a fixed backdrop. It is intimately entwined with motion, mass and spin. So far in our journey, we have seen rotation as the cradle of life, and now as a quiet sculptor of time. The universe spins, and in doing so, it not only shapes the climates of worlds, but also the rhythms by which clocks and processes unfold. The natural question that rises next is a simple one, but it reaches into every example we have touched. Why does spin persist at all? Once something begins to rotate, what keeps it turning from the smallest particle to the largest galaxy? What law lies beneath this deep preference for motion? To answer that, we will gently step toward a more unifying principle, a rule that hums beneath every spinning skater, every orbiting planet, every whirling star, the law that keeps everything turning. Out there in the dark world, spin stars, rotate galaxies, wheel slowly through the void. Close to home, the Earth turns under your feet, the moon circles above, and somewhere in the background, the Milky Way completes a vast orbit around its own center. From the smallest to the largest scales, the universe seems to have chosen a habit. Once things begin to move in circles, they tend to keep moving. If you listen beneath the details, there is a single quiet law humming under all this turning. It is not dramatic, it makes no sound, but it governs the way a child's toy spins on a kitchen table, the way planets trace their paths around the sun, and the way galaxies keep their graceful shapes for billions of years. It is called the conservation of angular momentum. Linear momentum describes straight-line motion mass times velocity. Angular momentum is a kind of rotational cousin, capturing how much turning a system has. When there is no external twist, no torque from the outside, angular momentum stays the same. It can change form. It can flow from one part of a system to another, but the total amount remains constant. The opposite happens when they extend their arms again. The spin slows. Angular momentum is still conserved. It is simply being expressed through a larger spread of mass, so the rate of turning can decrease. This same principle applies far beyond the skating rink. When a cloud of gas and dust in space begins to collapse under its own gravity, any small initial rotation it has will be amplified as it shrinks. As the cloud contracts, the material moves closer to the center, and like the skater drawing in their arms, the rotation must speed up to conserve angular momentum. Over time, the cloud flattens into a spinning disk. Stars may form near the center. Planets may assemble farther out. The entire system carries forward a portion of the original angular momentum, broken into orbits and spins of many bodies. Our own solar system shows the result. The Sun contains most of the mass, but the planets carry a large share of the angular momentum in their orbits. Each planet spins on its axis, and those spins are relics of earlier rotational motions in the disk, from which they formed, later modified by collisions and tidal interactions. Even the slight tilt of Earth's axis, which gives us our seasons, is thought to be the result of ancient impacts and the redistribution of angular momentum in the young system. Galaxies follow a similar script on a larger stage. In the early universe, matter was not perfectly still. It had small motions in different directions. As regions collapsed to form galaxies, those motions were converted into overall rotational spin. The enormous disks of spiral galaxies, with their arms gracefully curving around a bright center, embody angular momentum carried across vast scales. Once in place, that rotation is stubborn. Without an external torque, a significant gravitational interaction with another galaxy. For example, a galaxy will not simply stop spinning. Over long periods, encounters and mergers can change its rotation, sometimes dramatically. But the key is that angular momentum does not vanish. It is redistributed. Two spirals colliding may merge into an elliptical galaxy with a different pattern of motion, but the total angular momentum of the system, accounting for all its parts, remains conserved. The conservation of angular momentum also reaches down to the smallest scales we know. In quantum physics, particles, such as electrons, protons, and neutrons, possess an intrinsic form of angular momentum known as spin. Despite the name, this is not literally a tiny ball spinning in space. It is a more abstract property, but it behaves in many ways like angular momentum. It can point in different directions. It can add and subtract between particles. And in interactions, it is conserved. The total spin before and after a process must balance. This quantum spin is woven directly into the structure of matter. The fact that electrons have a specific spin, combined with the rules that govern how they fill energy levels in atoms, explains why elements have distinct chemical behaviors, why atoms arrange their electrons into shells, and why the periodic table has the pattern it does. The arrangement of electrons around atomic nuclei, guided by their spins, gives rise to the stability of matter, the bonds between atoms, and the complex chemistry that eventually supports life. In this way, the law of angular momentum conservation does not only describe the spin of planets and stars, it quietly shapes the architecture of atoms and molecules. The rotation you see in the night sky and the hidden spin in the particles that make up your body are linked by the same underlying principle. There is a particularly tangible way in which quantum spin touches your daily life, even if you never see it directly, the ticking of atomic clocks. Modern time standards are defined using the precise frequency of radiation associated with transitions between certain energy levels in atoms, often involving changes in the orientation of electron or nuclear spins. For example, the official definition of a second is tied to a specific transition in the cesium atom, a tiny adjustment in its internal angular momentum state that produces radiation with an extremely stable frequency. By counting those oscillations, atomic clocks keep time with incredible accuracy, losing or gaining less than a second over millions of years. That stability comes from the regularity of quantum systems obeying conservation laws. Even as planets drift and human societies change, the microscopic dance of spins in atoms provides a steady metronome. The law that helps keep galaxies turning also underlies some of the most precise tools we have for measuring time. When you realize this, there is a calm sense of unity. The rustle of leaves in the wind, the swirling of a hurricane, the orbit of the moon, the rotation of the Milky Way, the behavior of electrons in a crystal lattice, all of them exist within a universe where angular momentum is carefully balanced. Motion can change shape, but not the total measure of its turning. A spinning star may collapse into a tighter, faster spinning neutron star. A pair of orbiting black holes may spiral together and merge, sending ripples through space-time. In every case, if you could track all the angular momentum before and after, including what is carried off in gravitational waves and other radiation, the totals would match. In your own body, you can find echoes of this law as well. When you sit in a swiveling chair and push lightly against a desk to spin yourself around, you are exchanging angular momentum with your surroundings. The chair and your body pick up rotation in one direction. The building and the Earth, in principle, pick up an infinitesimally small rotation in the opposite direction, so that the overall balance is maintained. It is not something you will ever notice, but the bookkeeping of the universe keeps track of it faithfully. There is a gentle reassurance in knowing that nothing spins alone. Every rotation is part of a network of motions linked by this shared conservation. Even when a system seems isolated, a planet turning in the void, its angular momentum is part of a larger story that includes the material from which it formed, the interactions it will have, and the environment it inhabits. Of course, in reality, there are interactions. Tidal forces between Earth and the Moon transfer angular momentum from the Earth's rotation to the Moon's orbit, gradually slowing our planet's spin and causing the Moon to drift away a tiny amount each year. Gravitational encounters between stars can alter their orbits. Galaxies tug on each other, exchanging momentum as they pass and eventually merge. But again, at each step, the total angular momentum of the combined system remains conserved. The law does not prevent change. It simply ensures that change follows certain constraints. Lying here feeling still while the world turns, you are part of this vast bookkeeping. The atoms in your body carry intrinsic spin. Your movements exchange angular momentum with the environment. The planet that supports you continues to rotate, slowly bleeding some of its spin into the Moon's orbit. Above, the galaxy carries on its wide circuit around the cluster that holds it. All of this motion is different in scale and context, but it is unified by a common rule. Turning does not simply vanish, it transforms. As you let this thought settle, curiosity softens into a quiet appreciation. The cosmos is not a random scatter of swirling objects. It is a place where motion is guided, shaped by deep symmetries and their corresponding conservation laws. Angular momentum is one of those anchors linking the spin of electrons, the turns of planets, and the rotations of galaxies into one continuous story. In our journey so far, we have seen rotation emerge from the early universe, cradle life on a spinning Earth, bend time around massive bodies, and persist under the watchful balance of angular momentum conservation. Yet there is still more to understand, another layer of meaning that lies not in perfection, but in the breaking of it. And now, as the universe settles once more into quiet balance, may your thoughts drift gently among the stars. If you picture the universe in its earliest moments, it is tempting to imagine something perfectly smooth. No bumps, no edges, no directions. Just a uniform glow, filling all of space, every place, exactly like every other place. There is a certain comfort in that image, a sense of pure balance and order. But if the universe had stayed that way, perfect, unblemished, utterly symmetric, nothing interesting would ever have happened. No stars, no planets, no you lying here, listening. Perfection in this sense would have been a kind of silence. The story of motion, structure, and life is really the story of how that silence was broken. In physics, symmetry has a precise meaning. A system is symmetric when certain changes leave it looking the same. Imagine a perfect featureless sphere. You can rotate it any way you like, and it still appears identical. There is no preferred direction, no special point to mark. The laws of nature themselves exhibit symmetries. They do not care whether an experiment is done here or there today, or tomorrow facing north or south, as long as conditions are the same. This is why we can trust that a falling object will obey the same rules in one country as in another, or that light from a distant galaxy follows the same principles as light in your room. For each deep symmetry of the laws of physics, there is an associated conservation law, a kind of hidden promise. The fact that the laws do not change over time is linked to the conservation of energy. The fact that the laws do not depend on where you are corresponds to the conservation of linear momentum. Symmetry and stability walk hand in hand. Yet even in a symmetric world, a system can settle into a state that is less symmetric than the underlying laws allow. This is called spontaneous symmetry breaking. The rules remain balanced, but the specific arrangement the system chooses does not share all that balance. The early universe is thought to have gone through phases like this. When it was unimaginably hot and dense, certain forces that are now distinct may have been unified. As the universe expanded and cooled, it passed through critical thresholds where the underlying symmetries became unstable. Fields that once had zero average value across space acquired non-zero values, like the marble choosing a particular spot on the rim. The Higgs field, which helps give mass to fundamental particles, is one famous example of this kind of symmetry breaking. Once that field settled into a particular state, particles acquired their masses, and the familiar structure of matter emerged. Another, even more delicate breaking of symmetry appears in the balance between matter and antimatter. According to our best understanding, the Big Bang should have created particles and antiparticles in almost equal numbers. When matter meets antimatter, they annihilate, leaving only radiation behind. If the universe had been exactly symmetric in this way, nearly everything would have destroyed itself, and no ordinary matter would remain to form atoms, stars, or people. Yet here you are, made of matter, lying on a planet built from matter under a sky filled with stars radiating because of matter. This means that in those early moments there must have been a tiny imbalance, a slight tilt in favor of matter over antimatter. For roughly every billion pairs that annihilated, a single extra particle of matter remained. That small excess is what built the visible universe. Physicists call this mystery baryon asymmetry, and they have found hints that certain interactions among particles violate some symmetries in subtle ways. Processes that treat matter and antimatter almost but not quite identically can create the necessary imbalance as the universe evolves. The laws at their deepest level retain symmetry, Yet the way they are realized in the early cosmos produces a world in which matter wins by a hair. That hair's breadth of imperfection is the reason anything solid exists. All of this might sound abstract, but it can be felt in more familiar terms. A perfectly balanced pencil standing on its tip is a beautiful image, but it is also impossibly fragile. The tiniest vibration will cause it to fall, choosing some direction at random. Only when it lies on the table symmetry broken does it feel stable. The fall looks like a loss of perfection, but it is also a gain in reality. Before, the pencil was in a precarious ideal state that no real system can maintain. After, it occupies one of many possible but robust arrangements. Even the rotation of cosmic objects carries traces of asymmetry. A perfectly symmetric cloud of gas, with no motion at all, collapsing in a perfectly symmetric way, could in principle form a non-spinning star. But in reality, no cloud is exactly uniform. There are always small variations in density and velocity. As we saw earlier, those slight differences in motion amplified by gravity and conservation of angular momentum produce spin. Clouds flatten into disks, not because the laws demand disks, but because small imbalances make a disk the stable outcome. On a smaller scale, asymmetry is written into the molecules of life. Many biological molecules come in left-handed and right-handed versions, mirror images that cannot be superimposed. In non-living processes, these versions often appear in equal numbers, preserving symmetry. In living systems on Earth, however, only one-handedness tends to be used. Amino acids in proteins are almost always left-handed. The sugars in DNA are right-handed. Something in the chain of events from early chemistry to life broke the symmetry between mirror image molecules and stayed with that choice. The precise origin of this molecular handedness is still an open question, but some ideas involve asymmetric influences, such as circularly polarized light from stars, or weak force interactions that subtly favor one chirality over another. Whatever the mechanism, the result is another example of imperfection birthing structure. Life as we know it depends on this broken mirror symmetry. If you zoom out from these details and look at the pattern, a gentle insight comes into view. The universe is not messy because its laws are sloppy. The laws are elegant, symmetric, and deeply consistent. The mess, the asymmetry, the variety, those are what happen when you let those laws play out in a world where quantum fluctuations, cooling, and expansion push systems off their knife edges and into concrete states. You might think of it like a field of snow. Before anyone steps into it, the snow is smooth, uniform, pristine. The symmetries of the field and the snow's surface are intact. But it is also empty. Only when footsteps begin to trace paths, when sleds carve lines, and snowflakes pile unevenly on branches, does a landscape appear that you can live in, move through, and remember. The broken symmetry is not a flaw, it is the story. In terms of spinning, this means that rotation is not an enemy of order. It is one of the ways the universe moves away from sterile perfection into dynamic reality. Imperfections in density lead to gravitational collapse. Imperfections in motion lead to spin. Symmetry breaking guides fields into specific values that make particles, massive atoms, stable and chemistry rich. Every turn in the cosmos is rooted in some earlier imbalance, a marble that rolled a pencil that fell a field that chose one minimum among many. As you rest and think about this, a quiet emotional shift can happen. You might have grown up with the idea that perfection is the highest goal, that any deviation is a defect. Physics suggests something more nuanced. Too much perfection can mean nothingness, while small imperfections create the possibility for structure change and life. You are, in a sense, a tapestry woven from tiny departures from perfection. Those departures are not mistakes in the script. They are the ink that writes the script in the first place. The more you see this, the more the universe's spinning shapes and asymmetries feel less like chaos and more like a kind of cosmic handwriting. Each galaxy's tilt, each star's rotation, each planet's wobble carries information about how symmetry was broken in its past. The law of angular momentum ensures that these motions are conserved, but the way they are distributed tells a story of imprints, encounters, and choices made when the universe was young. We have now traced a path from perfect symmetry to broken symmetry, from sterile balance to dynamic complexity, from a universe that could have remained empty to one filled with spinning galaxies and living worlds. Along the way, we have seen that imperfection is not an accident layered on top of an ideal cosmos. It is the engine that made the cosmos interesting. The universe you inhabit is not perfect. It is better than that. It is alive with small necessary flaws, tiny broken symmetries that allowed everything to start moving, turning, and becoming real. Close your eyes for a moment and picture a spiral galaxy. A glowing disk of countless stars, blue and white near the edges, warmer gold toward the core, drifting slowly in the dark. The arms curve out in grand arcs, each one studded with clusters, nebulae, and traces of cosmic dust. The entire structure is turning slowly but surely, like a vast pinwheel made of light. Now imagine zooming outward far enough to see not just one galaxy, but millions. They appear like tiny whirlpools of starlight scattered across the black sea of space. And yet, for all their beauty, a mystery sits at the center of each one. Something unseen that keeps the stars from flying apart. That unseen presence is what scientists call dark matter. When astronomers began to measure how fast stars move within their galaxies, they expected a simple pattern. The closer a star is to the center, the faster it should orbit, pulled strongly by the concentrated mass there. The farther out a star lies, the weaker the gravitational pull, and so its orbital speed should drop. It's the same way that planets in our solar system move. Mercury close to the Sun orbits quickly. Neptune far away moves slowly. But galaxies do not follow that pattern. When Vera Rubin and her colleague Kent Ford observed the Andromeda Galaxy and others in the 1970s, they discovered something astonishing. The stars on the outskirts were moving just as fast as those near the center. The rotational speed of galaxies stayed almost constant across vast distances, defying the expectations of visible mass. If only the stars, gas, and dust we can see were responsible for the gravity, the outer stars should have long since flown away into space. Yet they remain bound, circling patiently in their orbits. The only explanation that fits the data is that something invisible, something with mass but not light, is holding them in place. This is the invisible hand of dark matter. Astronomers now believe that for every bit of ordinary matter that makes up stars, planets, and people there, are roughly 5 times as many particles of dark matter surrounding and shaping them. It does not glow, it does not absorb or emit light, but it exerts gravity. In computer simulations, galaxies form inside vast halos of dark matter, the visible stars tracing out only the inner shining core of a much larger invisible sphere. You can think of it as the scaffolding of the cosmos. Without it, galaxies as we know them could not have formed so gracefully. The luminous disks and spirals would be unstable, their stars too energetic to stay bound together for billions of years. With dark matter in place, the balance of gravity and motion settles into harmony. To visualize this, imagine the galaxy not as a flat wheel of stars, but as a whirlpool inside a deep, invisible basin. The basin is carved by the gravity of dark matter, The stars and gas swirl near the center, confined by the unseen depth. Without that depth, the water, the stars would spill outward. Even though we cannot see dark matter directly, we can observe its effects in other ways. When light from a distant galaxy passes near a massive object, the curvature of space-time bends its path. This effect, known as gravitational lensing, can magnify or distort the image of the background galaxy. By mapping these distortions across the sky, astronomers can trace where the hidden mass lies. What they find over and over again is that the majority of the mass resides not in the bright galaxies themselves, but in the invisible halos surrounding them, and in the vast cosmic filaments that link clusters together. The large-scale structure of the universe, its web of walls, filaments, and voids, is defined by the gravitational framework of dark matter. You could almost think of dark matter as the silent architect of form. It does not sparkle or burn, but it shapes where stars will gather and where emptiness will remain. Galaxies spin because the balance between centrifugal motion and the gravity of dark matter allows them to. The delicate dance of stars around galactic centers is choreographed by something that does not shine at all. The nature of dark matter remains one of the greatest open questions in science. We know how much there is and where it must be, but not what it is made of. The leading candidates are new kinds of subatomic particles, perhaps weakly interacting massive particles, or WIMPs that rarely collide with ordinary matter, or perhaps axions, ultralight particles that could form vast diffuse fields. Experiments deep underground and in space continue to search for tiny signals that might reveal dark matter's true identity, but so far it remains elusive. There is something poetic about that. The structures we see in telescopes, the great pinwheels of stars, the glowing clusters millions of light years across, are like illuminated patterns on the surface of an invisible ocean. The dark matter is the water itself, calm and deep, carrying the bright foam of galaxies upon its unseen waves. If you could see dark matter directly, the universe would look very different. The night sky would not be mostly empty blackness with a scattering of stars. It would be filled with faint, ghostly clouds of mass, weaving together into a giant, interconnected web. The galaxies would appear as bright nodes, where filaments intersect glowing beads in a cosmic net. In that image, you might sense both the enormity of the cosmos and its quiet cohesion. Everything we can see, every star, every planet, every atom of your body, is moving within a larger invisible framework. Your existence, your planet's orbit, even the slow turning of your galaxy, all depend on the gravitational field of something we cannot yet define. It's a humbling reminder that what we see is not the whole story. Just as Earth's spin goes unfelt and time's bending remains invisible to our senses, so too does dark matter work quietly in the background, shaping the visible universe without ever revealing itself directly. There is an emotional texture to that realization, a mix of wonder and acceptance. We live in a cosmos that is partly hidden by design. Light gives us a map of the surface, but not of the foundation. The unseen mass provides the structure, while the luminous matter paints its fleeting details. This pattern of something invisible giving form to what can be seen echoes throughout nature. In the human mind, thoughts shape expressions that others can observe but cannot measure directly. In the deep ocean, unseen currents sculpt the movements of waves on the surface, and in the universe itself, the unseen gravity of dark matter guides the luminous spirals of galaxies. You might wonder gently why the universe is built this way, why so much of it hides from light. No one yet knows. It could be that dark matter is an essential ingredient, born from the same quantum fluctuations that seeded the first galaxies. Or perhaps it is a sign that our theories of gravity are still incomplete, waiting for a deeper understanding. Whatever the ultimate answer, one truth remains clear. Without this invisible hand, the cosmos would look very different. Galaxies might never have formed stars, might never have ignited, and the spinning worlds that cradle life might never have existed. There is a quiet gratitude in that thought. We owe our existence in part to something we cannot yet see or touch, a substance that fills the space between galaxies, guiding them like a sculptor shaping clay in the dark. As the narration slows, you can imagine the camera drifting outward once more. The spiral galaxies recede, becoming tiny pinpoints in a web of faint light. Between them stretches the invisible structure of dark matter, its filaments humming with potential energy. The entire cosmos seems to breathe balanced between gravity and motion, darkness and light. And within that balance, another pattern begins to emerge. Because not only do galaxies spin under the pull of dark matter, but the very molecules of life within them seem to remember that turning. On the smallest scales, rotation reappears in the structure of DNA, in the twist of amino acids, in the handedness of living chemistry itself. The story of cosmic spin continues, descending now from galaxies to life's microscopic spirals, where the direction of rotation once again carries meaning. And so, from the vast invisible hand that holds the galaxies, we will drift next into the intimate architecture of living matter itself, the direction of life's spin, and the mysterious way it echoes the universe's oldest turning. Somewhere within the grand spiral of our galaxy, in the quiet outskirts of a star system, warmed by a modest sun, another kind of rotation has taken root. Not the vast, graceful turning of galaxies, nor the monumental spin of planets, but something smaller, something intimate, almost invisible. It is the rotation written into the molecules that make life possible. If you could look closely enough beyond cells and their organelles, past the atomic lattice of carbon and oxygen and nitrogen, you would find that life itself is built upon a spiral. Every cell in your body, every leaf on a tree, every strand of grass owes its existence to that elegant double helix DNA. It is a molecule made not only of chemistry, but of geometry, two twisting strands winding around each other in a slow, eternal dance. The shape of the double helix, discovered by James Watson and Francis Crick in 1953, is more than just a structure. It is a story of spin at the smallest scale. Each strand of DNA is composed of repeating units called nucleotides, molecules that link together like beads on a chain. When two strands come together, they coil in a right-handed spiral. This handedness is not arbitrary. Nature chose one direction over the other, a preference mirrored in many biological systems. If you were to reverse the twist, if DNA were left-handed instead of right, the entire architecture of life would change. Proteins might not fold correctly, enzymes might fail to recognize their targets, and the elegant choreography of replication would falter. Life, as it is known on Earth, depends on the constancy of that twist. This directionality is one expression of chirality, a term scientists use to describe asymmetry between left and right. The word comes from the Greek chair, meaning hand. Just as your left and right hands are mirror images that cannot be perfectly superimposed, many molecules exist in chiral forms. The difference may seem subtle, but in biology, it is everything. Amino acids, the building blocks of proteins, exist in both left and right-handed forms. Yet every living organism on Earth uses only the left-handed versions. The sugars that make up DNA and RNA, by contrast, are all right-handed. This mirror imbalance, this broken symmetry, runs consistently through every form of life we know. It is one of the universe's quiet mysteries. Why did life choose this direction? Chemistry alone does not dictate it. When amino acids are formed in laboratories or in space, they appear in roughly equal numbers of left and right-handed forms. But on Earth, from the smallest bacterium to the largest mammal. One-handedness dominates completely. Somewhere long ago, in the first pools of organic chemistry that predated life, a preference must have been established and locked in. Some scientists think circularly polarized light, whose electric field rotates in one direction, may have played a role. In certain star-forming regions, starlight becomes polarized by scattering through magnetic fields and dust. This light can selectively destroy one chiral form of a molecule slightly more than the other. Over long timescales, the difference builds up, favoring one orientation. If such molecules fell to Earth on meteorites, as many organic compounds did, they might have seeded the bias that life later amplified. Others propose that weak nuclear forces, which subtly distinguish between left and right at the level of subatomic particles, introduced a minute imbalance that cascaded upward into molecular biology. Still others suggest that once one chiral form gained even a tiny advantage, perhaps due to better stability or faster replication, it quickly dominated, eliminating its mirror competitor. Whatever the origin, the result is a kind of molecular memory. Every living cell today inherits the same bias chosen billions of years ago. Your DNA, twisting quietly in the nucleus of your cells, carries forward that ancient direction of spin, a choice made at the dawn of biology. And that choice, like so much in the universe, connects back to rotation itself. The same asymmetry that gives DNA its spiral form also shapes the larger motions of nature. Tornadoes and hurricanes twist differently in the northern and southern hemispheres because of Earth's spin. Seashells curl predominantly in one direction because of subtle developmental biases encoded in their chemistry. Even the embryonic heart begins to loop and turn in a specific orientation as it forms, establishing the body's left-right pattern. Spin, it seems, is not only mechanical, it is biological, woven into the very logic of growth. Even now, those same turning patterns shape existence. DNA coils into chromosomes. Proteins fold into spirals called alpha helices. Bacteria swim by rotating corkscrew-shaped tails called flagella. Plants twine upward around supports in spirals that trace the golden ratio. The spin of life repeats itself across scales, from the subcellular to the visible, from the invisible to the cosmic. There is a strange harmony in that repetition. The rotations of galaxies, the spins of planets, and the twists of DNA are separated by unimaginable differences in size and energy. Yet they all follow similar geometrical principles. They all embody balance through motion, a turning that stabilizes what might otherwise fall apart. A rotating planet balances day and night. A rotating electron stabilizes the atom. A twisting strand of DNA stabilizes the code of life. Spin is not chaos, it is order through movement. Scientists have even found that biological systems can synchronize with cosmic cycles in subtle ways. The Earth's rotation sets the circadian rhythms that govern sleep and wakefulness. Magnetic fields, generated by the planet's spin, influence the migrations of birds and fish. The gentle pull of the moon's orbit guides the timing of tides and the breeding of countless coastal species. You too are tuned to these rhythms. The cycle of day and night regulates your hormones, your heartbeat, your sense of time. The rotation of the planet beneath you quietly choreographs the ebb and flow of your biology. You are in a very real sense spinning with the Earth, not just physically but chemically and rhythmically. As you listen and breathe, your chest rises and falls in a slow oscillation mirroring the larger rotations that cradle you. In your body's symmetry, one hand, a mirror, of the other one lung larger than its twin, you can feel the echo of a deeper asymmetry that gave rise to all structure. The universe, it seems, loves to twist. From the swirl of galaxies to the spiral of your DNA. From the rotation of stars to the looping of your heartbeat. Motion is the language of existence. Each level reflects the same idea. Balance is not stillness, but motion perfectly sustained. You might take comfort in that thought as the narration slows. You do not have to be motionless to be calm. The Earth's rotation, the spin of its core, the cycles of your cells, all continue quietly as you rest. You are part of an intricate web of turning systems, every one moving in relation to another. The story of spin has carried us from the birth of the universe to the architecture of life itself. But even now the pattern continues. In the next quiet step, we will follow this motion back outward to the forces that keep everything turning together, the dance of gravity and light that maintains the universe's eternal equilibrium. For now, though, let your thoughts drift through the spiral of life. Picture a strand of DNA turning slowly in soft blue light, its twin helix gliding upward like smoke. Within that endless rotation lies the code of all living things, and in its geometry, the memory of the universe's first spin. Breathe, and let that spiral carry you outward once more, toward the cosmic forces that keep every rotation large and small, forever in motion. If you have ever watched a spinning top, you know how the story goes. At first it whirls with confidence, its edges blurred, its axis straight. Then slowly, almost imperceptibly, it begins to wobble. The spin slackens, the circle widens, and eventually the top succumbs to friction, tipping over and coming to rest. The universe, in its own way, tells a similar story. We live in an age where everything feels full of motion. Planets turn, moons orbit, galaxies spin. But the same laws that set things rotating also very gently draw energy out of those motions. Over immense stretches of time, spin's slow orbits change, and the cosmos drifts toward a quieter state. You can see the beginnings of this process right here on Earth. Our planet rotates once roughly every 24 hours, giving us our cycle of day and night. But that rotation is not perfectly steady. Tidal interactions with the moon raise bulges in Earth's oceans, and as those bulges lag behind the moon's position, friction between water and seafloor drains a tiny bit of energy from Earth's spin. That energy does not vanish. It ends up as a faint warmth in the tides. The cost is that Earth's rotation slows very slightly over time, and the moon, pushed by the transfer of angular momentum, drifts ever so gently farther away. Measurements of ancient eclipses and modern atomic clocks tell the same quiet tale. On average, the length of a day increases by a little over 0.02 of a second per century. It is such a small change that you will never feel it. Generations pass while the day stretches by a fraction of a heartbeat. Yet, across hundreds of millions of years, the difference accumulates. When dinosaurs walked the Earth, a day was noticeably shorter than it is now. Hundreds of millions of years from today, it will be longer. Meanwhile, the moon is slipping away at about 1.5 inches per year, the distance of a slow-growing fingernail. At that pace, in the far future, the moon will orbit at a greater distance, and the tides will weaken. Long before that, Earth's rotation and the moon's orbit may reach a kind of truce, with one rotation of our planet matching one orbit of the moon. At that point, the same side of Earth would always face its satellite, and the length of a day and the length of a lunar month would become the same. This process, tidal breaking, is not unique to Earth and the moon. Many moons in the solar system already keep the same face turned toward their planets. They have been tidally locked for eons. Their rotation slowed until it matches their orbital period. Some planets over long timescales can also become locked to their stars. In each case, friction and gravity act together to convert ordered rotational energy into heat, gradually simplifying the pattern of motion. From a distance, this might sound ominous, as if the universe were inexorably grinding to a halt. But in human terms, these effects are impossibly slow, stretched across spans of time so vast that they feel almost abstract. Earth's rotation will remain rapid enough to give us familiar days and nights for as long as our planet is habitable. The moon's retreat is gentle, like the slow tide of a cosmic ocean. Yet, if you step back even further beyond the scale of planets and moons, a more dramatic evolution comes into view. Galaxies too do not spin forever unchanged. They live in a universe where gravity always reaches out, where no island of stars is entirely alone. Over billions of years, galaxies tug on each other as they pass. Sometimes they merely distort one another. Sometimes they collide and merge their stars, weaving into new configurations. For a long time, astronomers thought it almost certain that our Milky Way and the neighboring Andromeda galaxy would collide head-on in about 4 or 5 billion years, merging into a single larger galaxy. Newer studies using data from the Hubble Space Telescope and the Gaia mission suggest the picture is more nuanced. There is still a strong chance of a future merger, roughly even odds over the next 10 billion years, but the exact timing and manner are uncertain. Whether the encounter is direct or more glancing gravitational interactions will eventually reshape both galaxies. Their dark matter halos and stars will swirl together, forming a new structure with a different overall spin. Some stars may be flung onto long looping orbits. Others may end up in a more rounded, slowly rotating cloud. The total angular momentum of the system will be conserved. But much of the ordered disk rotation we see today will be stirred into more diffuse motions. On even longer timescales, as galaxies continue to interact and merge, the universe's overall pattern of motion grows more subdued. The sharpness of spiral arms fades. The bright star-forming disks give way to larger, more featureless galaxies where star formation has mostly ceased. The gas that once cooled and condensed into new stars becomes exhausted or heated, unable to collapse further. The cosmic fireworks of bright young stars become rarer. Cosmologists have traced this trend in observations of galaxies at different distances, which correspond to different times in the universe's past. The rate of star formation peaked billions of years ago and has been declining since, like the fading of an enormous slow-burning fire. This decline is part of a broader journey driven by the second law of thermodynamics, the principle that in an isolated system entropy, the measure of disorder tends to increase. The universe began in a state that, while hot and dense, was surprisingly uniform. Over time, gravity created structure galaxies, stars, planets. Those structures released energy, lighting the cosmos with starlight. But as energy is radiated away and spread out, the universe moves step by step toward a state where temperature differences diminish, where useful energy becomes scarce. The heat death of the universe is one name for this possible final state. In that distant future, if the expansion of space continues and accelerates, galaxies will drift so far apart that their light can no longer reach each other. Stars will exhaust their fuel and wink out one by one. White dwarfs, neutron stars, and black holes will dominate, slowly cooling or evaporating over inconceivably long periods. Eventually, if this picture is correct, the universe will approach a condition where energy is so evenly distributed that no more work can be done. No more engines can run, no new structures can easily form. It is a scene so remote in time that it stands more as a philosophical boundary than a practical concern. Numbers like 10 to the power of 78 years, one followed by 78 zeros, are so large that they slip beyond intuition. Compared to these spans, the entire history of life on Earth is the briefest flash, a single breath in a long, slow exhale. Still, there is a gentle tension in contemplating this trajectory. We are used to cycles, day following night seasons, returning patterns that repeat and renew. The idea of a cosmic story that slowly runs down, that moves toward a state where nothing much happens, can feel unsettling at first. But here, too, perspective offers a kind of peace. The universe is not racing toward its end. It is drifting there with unfathomable patience. For billions upon billions of years to come, stars will still shine, planets will still turn, and the remnants of galaxies will still move under gravity's pull. The eventual quieting of motion is not a sudden shuttering of lights, but a long gradual dimming, a twilight stretched across timescales so vast that they almost cease to be times at all, turning into shapes in thought rather than experiences. And even in that imagined final state, motion may not disappear entirely. Particles will still drift. Fields will still fluctuate. At the smallest scales, quantum jitters may continue, tiny echoes of the universe's restless nature. What fades is not movement itself, but the organized flows of energy that power stars, planets, and life, those great, structured motions that we are part of now. Right now, you and everything you know exist near the crest of that arc. Galaxies are still bright. Stars like the sun still burn steadily. Planets still have active interiors, atmospheres, and climates. Life has emerged, at least, on one world, able to contemplate these grand patterns. The spins we have been tracing, from electrons to planets, from galaxies to the universe's fate, are all still active, still shaping reality in vivid ways. As you breathe softly and listen, you occupy a moment when the cosmos is richly structured and full of turning. You are carried on Earth's rotation, warmed by a star that still has billions of years of fuel embedded in a galaxy whose long-term dance with its neighbors has only just begun. The distant heat death, if it comes, will be the closing of a story that is still in its middle chapters. In that sense, the slow fading of motion is less a threat and more a reminder of how precious the present is. The fact that we live in an era of abundant structure and energy where complex systems can arise and persist is itself remarkable. The universe did not have to be this way. A slightly different balance of laws or initial conditions could have led to a cosmos that was brief, quickly smoothed into uniformity, or too chaotic for long-lived structures to form. Instead, here we are, conscious beings on a spinning planet, able to look back toward the beginning and forward toward possible ends, and to feel something about both. As our journey nears its final turn, a gentle idea begins to surface. If motion will one day fade, what if anything remains of its memory? We have seen how angular momentum carries information about past events, how spins and orbits encode the history of forces and interactions. We have seen how broken symmetries give rise to the structures that remember them. Perhaps then there is something about us, about life and awareness, that also remembers, not in the sense of filing away facts, but in the deeper sense of embodying the universe's long history of turning, collapsing, and evolving. If you sit very quietly for a moment and simply notice yourself, something gentle becomes clear. Your chest rises and falls. Your heart beats with a soft, persistent rhythm. Thoughts appear and dissolve. Even in stillness, you are full of motion. Deep inside your body, countless processes are unfolding at once. Blood flows in branching rivers. Electrical pulses travel along nerves. Molecules collide, transform, and rearrange. Your lungs fill and empty. Your eyes make tiny movements even when you stare at a single point. To be alive is not to be still. It is to host an orchestra of coordinated motion. On the most basic level, the atoms that make up your body are themselves small archives of movement. Their nuclei hold protons and neutrons together through the strong nuclear force, while electrons occupy diffuse orbitals, quantum clouds, whose shapes are set partly by angular momentum and spin. Those electrons possess intrinsic spin, a fundamental kind of angular momentum that cannot be removed, only redirected or recalculated. The very stability of the atom, the way it binds and interacts, depends on this rotational character. Every carbon atom in your bones, every oxygen atom in your blood, every nitrogen atom in your DNA carries this hidden angular momentum inherited from the deep rules of quantum mechanics. These atoms were forged in earlier generations of stars, which themselves spun as they burned. Before those stars, the raw material of your body was part of swirling clouds of hydrogen and helium, born from the early universe's expanding, rotating structures. In that sense, you are not separate from the cosmos. You are made of it. The spins of fundamental particles, the rotations of atoms, the orbits of electrons, all of them are direct descendants of the angular momentum that emerged after the Big Bang. Those motions did not vanish. They condensed into you. But something additional happens in living systems. Motion becomes not only conserved, but organized into patterns that can respond, adapt, and eventually become aware. Consider your heart. It is more than a pump. It is a rhythmic engine, contracting and relaxing in waves that travel across its muscle fibers. Those waves are guided by specialized cells that act as pacemakers, generating electrical pulses that spread in a precise order. The result is a steady beat, a repeating cycle of motion that began before you were born and will continue reliably and tirelessly for as long as you live. Your brain, too, is a landscape of rhythms. Billions of neurons exchange signals through electrical spikes and chemical messengers. When many of them coordinate, they form brain waves, oscillations at different frequencies that shift as you wake, focus, relax, or drift toward sleep. Alpha waves rise when you close your eyes and rest. Slow delta waves roll through the brain in deep sleep. Faster gamma rhythms appear when networks synchronize during certain kinds of perception and memory. These oscillations are not decorative. They help time the flow of information, binding together distant regions into coherent experiences. In this pulsing exchange, the brain continually constructs a model of the world and of the self, a flowing pattern of activity that you experience as awareness. When you remember something, when you notice the sound of your breathing, when you feel a quiet emotion rise and pass, you are participating in a complex choreography of motions that began long before you. The atoms in your neurons hold spin. The molecules in those neurons bear the chiral imprints of ancient chemistry. The roots of those atoms go back to earlier stars, and the angular momentum of those stars goes back to the first swirling clouds. Step by step, the chain leads back to the tiny fluctuations in the early universe, magnified by cosmic expansion, shaped by gravity, and translated into spin at every scale. This idea can stir a brief tension inside. We are used to thinking of ourselves as separate observers standing apart from the universe and looking at it as something external. The notion that we are the universe, looking at itself from within, can feel disorienting. But if you stay with it gently, the tension softens into a sense of belonging. The conservation of angular momentum means that motion carries the memory of its origins. The spin of a planet remembers the rotation of the disk that formed it. The rotation of that disk remembers the angular momentum of the cloud that collapsed. The motions in that cloud remember the direction and magnitude of early fluctuations. Following the thread backwards, your own movements and the spins of the particles composing you encode information about events spanning billions of years. You may not be able to read that information directly, but physics can. By measuring the spins and orbits of stars in a galaxy, astronomers can infer how that galaxy formed and evolved. By studying the distribution of angular momentum in planetary systems, scientists can reconstruct aspects of their birth. In the same way, if someone could examine every detail of motion in your body, down to the quantum level, they would find embedded in it the full story of cosmic history, from primordial plasma to nuclear fusion, to planetary chemistry, to evolution. Within that story, consciousness is like a special kind of echo. It is not just the continuation of motion, but the awareness of motion. When you lie still and think about the Earth's rotation, the Sun's orbit, and the universe's expansion, you are using patterns of motion in your brain to hold and examine patterns of motion outside your body. You are, in effect, a moving system, reflecting on the movements that created it. In this sense, you are the universe, remembering its own motion. That does not mean there was a purpose laid out from the beginning, or that the cosmos intended to produce minds. As far as we can tell, the universe follows its laws, without preference, letting possibilities unfold wherever conditions allow. But among all those possibilities, there are some in which matter organizes into patterns capable of awareness. You are living proof that at least one such arrangement exists. There is a quiet beauty in the idea that memory in the broadest sense is always physical. A footprint in sand remembers a step. A fossil remembers a living creature. Tree rings remember seasons of growth. The angular momentum of a spinning galaxy remembers the distribution of mass and motion in the cloud from which it formed. The structure of your brain and the patterns of connectivity between neurons remember your experiences. In all of these cases, motion and change leave traces. The universe writes its history into its current state. On the largest scales, that history is carried in the distribution of galaxies, the background radiation, and the spins of clusters and stars. On the smallest, it is carried in the quantum states of particles and fields. Somewhere in between, in your own body, it is carried in the rhythms of heart and brain, in the chirality of molecules, in the cycles of sleep and waking tuned to Earth's rotation. What makes you unique is that you can feel this. You can sense your own rhythms. You can picture the spinning Earth, the turning galaxy, the fading light of distant stars. You can imagine futures you will never see, and pasts you never experienced, using the subtle dynamics of neurons to simulate motions that lie far beyond your physical reach. When you gaze up at the night sky and feel a quiet shiver of wonder, something profound is happening. Atoms forged in long-dead stars, arranged into a living nervous system, by evolution, are using their inherited motion to contemplate those same stars and the laws that shape them. The universe's capacity for movement has in you become a capacity for curiosity. If you let that realization settle gently, it can bring both humility and comfort. Humility, because you are one small configuration among countless others, a fleeting pattern in a vast ancient sea of motion. Comfort, because that pattern is deeply connected to everything around it. You are not an outsider peering in. You are a local pattern of the universe's unfolding, briefly conscious of itself. Even your desire to understand, to listen to explanations about spin and symmetry and dark matter, is part of this process. It is the universe's own restlessness, expressing itself as questions in your mind. The answers are never complete, and that is all right. The act of wondering is itself a kind of participation in the cosmic dance. Meanwhile, outside your window, Earth continues to turn. The planet carries you through space at tremendous speeds, all of it arranged so smoothly that you can rest without feeling the rush. The galaxy turns more slowly still, its stars voyaging around the center over hundreds of millions of years. Somewhere in that center, a supermassive black hole spins, dragging space-time around it. The large-scale structure of the universe is expanding filaments of dark matter stretching galaxies, receding from one another. Against that backdrop here, you are lying, still breathing, listening. Within your stillness, countless tiny motions continue. Your cells repair. Your brain slides gradually towards sleep. The story of cosmic motion, traced from the earliest times through stars and planets and life, has reached this moment, this breath, this heartbeat, this thought. If you feel very quiet inside, you might imagine all of these layers of motion lining up: the spin of electrons, the twisting of DNA, the beating of your heart, the firing of your neurons, the turning of Earth, the orbit of the moon, the path of the planet around the sun, the rotation of the galaxy, the expansion of the universe. None of them is separate from the others. All are entwined in a single continuous flow. You do not need to hold all of this consciously. It is enough to know softly that you are part of it. As you drift toward rest, the universe will continue to move, just as it did before you were born, and just as it will after you are gone. Your awareness is a temporary clearing in that flow, a brief opening through which the cosmos can look at itself and feel for a while what it is like to be here. So, let your breathing slow. Let your thoughts loosen their grip and become lighter, like leaves turning in a gentle current. The spins and orbits that made you will keep their quiet watch. The conservation laws and broken symmetries that scaffold reality will continue to hold. The universe will go on, remembering its motion in countless ways, in stars, in galaxies, in the atoms of distant worlds, and for a little while longer in you. And now, as the stars continue their silent revolutions and the Earth carries you gently through its nightly spin, feel the vastness of motion that holds you. Every breath you take, every heartbeat, is part of the same rhythm that turns galaxies and stirs the oceans. You are not outside of this movement. You are its living memory, the universe remembering its own motion for a fleeting moment in time. Rest, knowing that the same forces that shape the cosmos cradle you now in their quiet balance. If you enjoy drifting through journeys like this, stay a while. Let curiosity guide your dreams. There's always more to explore, more wonder to find waiting softly among the stars.